Good evening, everyone. So today in this class, we'll be discussing about the Gauss law. In the last class, we discussed about the electric flux through any surface, right? But in this class, we'll be particularly dealing with the flux passing through the closed surface, right? In the last class, we discussed about the flux passing through the open surfaces and closed surfaces as well. But today in this class, we'll be discussing more about the electrostatic flux through closed surfaces, right? So Gauss law is applicable for, if we talk about the Gauss law, it's only applicable for closed surfaces. Applicable for closed surfaces. What do you mean by closed surface? The closed surface is that surface which encloses a volume, right? Which encloses a volume. Like we have a sphere, it's a closed surface because it encloses a volume, correct? And we have a cube, it's also a closed surface. Cuboid, it's also closed surface. Cylinder, it's a closed surface, right? So all these closed surfaces, all these shapes, these are the closed surfaces, right? They enclose the volume within it, right? If we take example of a square, right? Square is not a closed surface; it's an open surface, right? Because square does not enclose any volume, right? Similarly, rectangle is an open surface, right? Triangle is an open surface, right? So, Gauss law particularly is applicable for the closed surfaces, right? It's a very important point here for the Gauss law to be applicable. The surfaces should be closed one. The surfaces should enclose a volume, right? So it means that a closed surface means surfaces enclosing volume, right? Surfaces enclosing volume. Surface enclosing volume. Correct. So what the statement actually, what the Gauss law actually states is that suppose that we have any imaginary surface, right? Any imaginary but closed surface. Any imaginary closed surface. Let's suppose that uh, this is our any imaginary surface, right? This is our imaginary closed surface. This is our imaginary closed surface. This is our imaginary closed surface, right? So Gauss law states that in a closed imaginary surface, suppose that the charge enclosed by this closed surface are like Q1, Q2, Q3, and suppose there can be a charge also outside this closed surface, right? Q4, Q5, or Q6, right? Gauss law states that the total flux through this closed surface, right? Total flux through this closed surface, it only depends, the total flux through this closed surface, Gauss states that in an imaginary closed surface, in an imaginary closed surface, total flux is equal to 1 upon epsilon or times 1 upon epsilon or times the charge enclosed by the surface. Charge enclosed by the surface, right? So it means that whatever the total flux through this imaginary closed surface, it only depends upon the enclosed charge. It only depends upon the enclosed charge, right? So it only depends upon the charge enclosed by the closed surface. So whatever may be the charge present outside, right? Whatever may be the charge present outside this closed surface, it doesn't depend. It doesn't matter, but it only matters. It only depends upon the charge enclosed in a closed surface, right? So it means that suppose that Q1, Q2, and Q3 here are the charge enclosed, correct? Q1, Q2, and Q3 are the charge enclosed here. right? So these are the charge enclosed. So it means that if we have to the phi through this closed surface, phi closed surface is nothing. It will be the charge enclosed upon the epsilon naught, right? So this is nothing. This is the this is the Gauss law, right? This is the Gauss law. So this is the statement of Gauss law. So this is the mathematical statement of Gauss law. What is this? This is nothing but Gauss law. This is Gauss law, correct? So in this case, if we look at the situation right here, we have an imaginary surface, and in this imaginary surface, Q1, Q2, Q3 are the charge enclosed inside the surface, right? Q1, Q2, Q3 are the charge enclosed in this surface. So phi through this closed surface will be nothing. That will be equal to Q1 plus Q2 plus Q3, right? Over epsilon. So this will be the total flux through this closed surface, and this total flux will not depend upon the charge Q4, Q4, Q5, and Q6, right? Now Q1, Q2, Q3 is the total Q1, Q2 plus Q3 upon epsilon naught is the total flux through this closed surface, right? So we also said that this Gauss law is applicable only for closed surface. So this flux is nothing. It's the flux which we calculate over the closed surface, or we can rewrite it as we know flux is nothing. It's the integral of E dot ds, right? It is the integral of E dot ds, correct? Is the flux through the surface, but this represents the flux through closed as well as open surfaces, right? This represents the flux through closed as well as open surfaces, but in case of Gauss law, the surfaces are closed. So we'll just write the closed integral here, right? So it will be equal to charge enclosed upon the epsilon naught, charge enclosed upon the epsilon naught, right? So it will be charge enclosed upon the epsilon naught. So this is another form of Gauss law that we can write, that flux through the closed surface is nothing, it's charge enclosed upon the epsilon naught. So this closed integral has an important significance, that it means that we're talking about the closed surfaces. It means that we're talking about only for those surfaces which enclose volume, right? If the integral would have been open integral, right, it would if the integral is like this, suppose that if the integral is like this, that's integral of E dot ds, right? It's integral of E dot ds. So it is applicable for both closed as well as open surfaces. Closed as well as open surfaces, right? Closed as well as open surfaces. But this integral is specific for the closed surfaces, right? This is specific for closed surfaces. Right. So Gauss law is nothing. Closed integral over the surface, closed integral of the electric field over the surface is nothing, that's equal to charge enclosed upon the epsilon naught, right? So this is our Gauss law, right? So one more important point about this integral is that this electric field E, we know that in this case, in this closed surface, like right here, well, this is our closed surface. This is our closed surface. We have charge Q1, Q2, and Q3 here, and we can have also charge Q4, Q5, and Q6 here outside this closed surface. Now there are six charges. Three charges are present inside the closed surface, and the three charges are present outside this closed surface, right? So in this case, this electric field is due to all the charges, right? Due to all the charges. Due to all the charges present inside as well as outside of the closed surface. This electric field E is due to all the charges present inside, due to all the charges present inside as well as outside the closed surface, right? Correct. So due to all the charge present inside as well as outside the closed surface. But this flex in this case, the second form is that this phi due to on this closed surface is nothing that's the charge enclosed upon epsilon naught. So this flex is only because of the enclosed charge, right? Enclosed charge. It's only because of the enclosed charge. So does it mean that the outside charge does not contribute to the flex? Yes, exactly. They do not contribute any flex to the to this surface or any surface, right? Because the total flex linked because of these outside charge will be always zero. Because whatever be the flex entering because of these charge Q4, Q5, and Q6, same amount of flex will be leaving the closed surface, right? It means that there will be no contribution of the flux because of this. There will be no contribution of flux because of this Q4, Q5, and Q6 because same amount of flux will be entering through this closed surface and the same amount of flux will be leaving the surface, right? So the net contribution by this Q4, Q5, and Q6 towards the flux of this closed surface will be equal to zero. But the electric field, but the electric field, but the electric field is due to all the charge. It's due to Q1, Q2, Q3, and all the charge present outside as well. So this is a very important point with respect to the Gauss law. The electric field is not only because of the inside charge, so because of both inside as well as outside charge. So it gives us the net electric field due to all the charge present inside as well as outside the closed surface, right? And let's suppose if a closed surface, if a closed surface is placed in a uniform external field, right? Uniform external field, correct? Then the total flux, then the total flux to the surface will always be zero, right? Always be zero. Let's suppose that we have a sphere here. This is the sphere. This is our sphere. And where there is an external uniform field, external electric field, which is crossing this sphere, right? There's nothing, this is a sphere. Provided there is no charge. There is no charge enclosed by this sphere, right? There's no charge enclosed by this sphere. And what we are doing is that in on this sphere, the electric field lines are entering as well as leaving this sphere, right? But this electric field is nothing. This electric field is nothing. It's uniform. It can be uniform as well as non-uniform. But in this case, we are discussing about the uniform field, right? This is the uniform field. So it means that integral of E dot ds will be equal to charge enclosed, right? Charge enclosed upon epsilon naught, right? Charge enclosed upon epsilon naught, correct? Or we can say the flux, total flux is nothing. It's the integral of E dot ds, right? To this closed surface. We know that this E is nothing. It's uniform. We can take it outside the integral because it is constant, right? That's ds vector. Now, integral of ds vector for a closed surface, right? For a closed surface, for a closed surface. If the surface is closed, then integral of ds vector, that's the area vector, is always going to be zero, right? It's always going to be zero because suppose if we take this element of ds vector here, this element of ds vector here, it will be directed along this direction, along the normal away from it. And similarly, there will be another ds vector here. that will be of same magnitude, but it will be directed like this, right? We can see that this ds vector and this ds vector will cancel out each other. It means that overall the integral of ds vector over a closed surface will be 0. And this, if we take one more element, this is ds here, it will be directed along this direction, right? And this is also ds here, it will be directed along this direction, correct? So they will be cancelling out each other. So the net summation of this ds vector will be equal to 0, right? So for any closed surface, the integral of closed area vector is nothing, it's equal to 0, right? If this is 0, it means that flux is 0. Flux will be 0. So this is the reason why the flux through the closed surface will be always equal to 0, right? Will be equal to 0. So in case of non-uniform field, right? In case of non-uniform field, let's suppose that a closed surface, a closed surface is placed in an external non-uniform field, right? External non-uniform field, right? Let's suppose we're once again taking this closed surface, that's the sphere here, that's the sphere. So sphere is our closed surface, it's nothing, it's sphere here. And let's suppose non-uniform electric field can be like, if we have a plus q charge here, then the electric field because of this plus q charge will be a non-uniform electric field, right? Like this. It's not a uniform electric field. So this will be a non-uniform electric field through this sphere, right? You can write it as non-uniform field, right? This is nothing, it's non-uniform electric field, correct? So we know that if we apply the Gauss law is nothing, it's the charge enclosed upon the epsilon naught, right? The total flux through this sphere will be nothing, it will be the charge enclosed upon the epsilon naught. And we know that the charge enclosed by this sphere is once again 0. There is no charge inside this sphere. So it means that the total flux will once again be equal to 0, right? Total flux will be once again equal to be 0, right? There will be no contribution of flux on the closed surface because of the outside charge, right? So be it uniform field, be it external uniform field, or be it external non-uniform field, the flux through the closed surface is always going to be 0, right? External uniform or non-uniform field does not contribute to the total flux, right? Through the closed surfaces, right? So the total flux will be then once again equal to 0. One more important point is that let's suppose uh, this is the shape of Gaussian surface, right? And this can be the shape of Gaussian surface, right? Or this can be the shape of Gaussian surface, right? Let's suppose if we in this closed surface, if we place a charge q1 here, here we can place a charge q2 here, here we can place a charge q3 here. If the total flux is to be calculated in case A, case B, and case C, right? The total flux will be nothing. It will be simply charge enclosed upon epsilon naught. And the phi 2 here will be nothing. It will be charge enclosed, that's q2 upon epsilon naught. In the case 3, it will be nothing. It will be charge enclosed, that's q3 upon epsilon naught. So it means that phi is independent of it's independent of position of charge, independent of position of charge. It's independent of position of charge inside Gaussian surface, right? Inside Gaussian surface. Inside Gaussian surface. So it does not depend upon the position of the charge inside the Gaussian surface. It can have any position inside the Gaussian surface. It can have any position inside the Gaussian surface, and the flux will be independent of the charge position of the charge inside a Gaussian surface, right? And similarly, the flux will also be independent of shape and size of a Gaussian surface. The total flux, it doesn't matter whatever be the shape and whatever be the size of Gaussian surface, right? So flux will be still independent of shape and size of a Gaussian surface, right? So we can write here phi is also independent of shape and size of Gaussian surface. Shape and size of Gaussian surface, right? So it will be independent of shape and size of a Gaussian surface. Let's move on to the next point. Suppose that if we place an imaginary closed surface inside the Gaussian surface, imaginary closed surface, and it is placed in the external electric field, right? This imaginary surface is placed in the external electric field, and suppose that because of the external electric field, the net flux through this Gaussian surface is non-zero. So if because of the external field, because of the electric field, net flux, net flux, net flux through the closed surface is non-zero, right? Is non-zero. If the net flux through the closed surface is non-zero because of the electric field, then it must enclose some charge. Then it must enclose some charge. Then it must enclose some charge. If the net flux through the closed surface comes out to be non-zero, right? Then it's only possible if this closed surface is actually enclosing some charge, right? Otherwise, it's not possible. It must enclose some charge, right? For the net electric flux to be non-zero, right? For the electric flux to be non-zero. So if net electric flux is coming out to be non-zero, it means that this Gaussian surface is actually enclosing some charge, right? Now, if the enclosed is zero, if the total charge enclosed is zero, let's suppose that this is our Gaussian surface, right? This is our Gaussian surface. This is our Gaussian surface. In short, I write it as GS. That's nothing. That's the Gaussian surface. Suppose that uh, this is the charge Q here, and we have placed equal amount of minus Q charge. Now we can say that the flux is nothing. Flux is nothing. It's Q minus Q upon the epsilon naught. So the total flux through this Gaussian surface is nothing. That's equal to zero, right? Uh, Total flux through this closed surface is equal to zero, right? Now we can also rewrite it as integral of E dot ds, right? Integral of E dot ds. That's equal to zero, correct? So if the total flux is zero, it doesn't mean the electric field is zero, right? Remember this point. It doesn't mean the electric field is zero. If phi is equal to zero, E may or may not be zero. E may or may not be zero, right? Correct? So if the total flux is equal to zero, then the electric field may or may not be zero. It's not necessary if the total flux is zero, then electric field is going to be zero, right? Electric field, if the total flux is zero, then electric field will be zero only in some special cases, right? It can have a non-zero electric field, right? Let's suppose that this is the charge Q1, this is the charge Q here, and this is the charge minus Q here, right? And this is our Gaussian surface, right? This is our nothing, this is the Gaussian surface. Let's suppose that. If we calculate the electric field at this point, because of this charge Q, the electric field will be in this direction, right? Let's call this electric field as EQ. And because of this charge minus Q, the electric field will be in this direction, right? That's E minus Q, right? E minus Q. It means that on this Gaussian surface, the net electric field will be along this direction, right? This is the E net, which is non-zero, right? Which is non-zero. So it means that even if the flux is equal to zero, the electric field is non-zero. So it's not always like that. If the flux is zero, the electric field is going to be zero, right? So let's try to calculate the flux through some surfaces, through some imaginary closed surfaces. And let's try to solve it. The question here is, we have a question number one here. Find the total electric flux through cube and flux through each of cube and also flux through each corner, right? So what we have to calculate is that we have to find the electric flux through this cube and electric flux through each face of this cube, right? The total electric flux through each face of this cube is going to be nothing. It's a closed surface that will be the charge Q enclosed upon the epsilon naught, right? So phi will be equal to charge Q upon the epsilon naught, right? And we know that this charge Q here, this charge Q here is symmetrically placed, right? It is symmetrically placed. It is symmetrically placed here inside this cube at the center of this cube. It means that this flux will be equally distributed to all the six faces, right? This flux will be equally distributed to all the six faces. So we can say that the flux through phase will be equal to nothing. It will be charge Q upon epsilon naught, and all the flux will be distributed equally through all the six faces, right? So upon 6. So Q upon 6 epsilon naught will be the total flux through each phase, right? Through each phase. And let's discuss another situation. Let's suppose that this is our square here. This is our square here. This is the square here, right? This is the square here, right? And we are placing a charge Q at the corner of the square. The Q charge is placed at the corner of this sphere, right? At the corner of this square, not sphere, at the corner of this square. So the Q charge is placed at the corner of this square. We have to calculate, find the flux, find the flux through this, find the flux through the square. We have to find the total electric flux through this square, right? So this charge Q is placed at the corner of this square. We can say that the electric field due to this charge Q will be symmetrically some electric field lines will be passing parallel to the plane of this square, right? Like this. And some electric fields will be like this. They will be at an angle of this plane. Means that the electric field lines will be out of this plane. They will not be in this plane, right? The only electric field lines because of this charge q, which will be in this plane, that will be parallel to this plane. It means that there will be no electric field line because of this charge q, which will be entering this square, right? There will be no electric field line because of this charge q, which will actually pass through this square, right? So these will be the electric field lines through this corner, right? So actually no electric field line will be passing through this square, right? It means that if the no electric field is line passing through this square, it means that the net electric flux through this square when the charge is placed at the corner of a square will be equal to zero, right? So the net flux will be equal to zero. So phi net will be equal to zero. And let's suppose that we have another situation. Suppose that this is our cube. This is our cube here. And at the center of the face of this cube, at the center of the face of this cube, right, on one of the faces, right, we are placing a charge cube. We are placing a charge cube. We have to calculate the flux through the cube. Flux through the cube. Flux through the cube is. Flux through the cube is. We can see that this charge q is not placed symmetrically here, right? Because this charge is placed at one of the faces of cube, but not symmetrically placed, right? We can do one thing. Let's make another cube here, right? Like this. So we can divide this cube into two equal cubes, right? We can divide this cube into two equal cubes. Let's divide this cube into two equal cubes. This is our another line. This is the third line here. So this is the third line. This is the last line here. Now you can imagine that these are the two cubes actually, right? These are the two cubes actually, right? Each of the cube is actually sharing the same face, right? Common face, right? They're sharing the common face. And at the center of this face, we are placing a charge cube. At the center of this face, we are placing the charge cube. It means that the electric flux because of this charge q will be actually equally divided between the two cubes, right? It will be equally divided between the two cubes, right? Independent of the size of the two cubes, right? Whatever be the length of the side of the two cubes, right? It doesn't matter. But if this charge q is symmetrically now placed between the two cubes and having both the cubes are having the common face, right? And at that face, we are placing a charge q at the center of that face, then the flux will be equally divided, right? So in the whole of this cube, the total flux will be nothing. It will be charge enclosed, that's q upon epsilon naught, and this flux will be equally divided between these two cubes. So we can say that flux through each cube will be equal to q upon 2 epsilon naught, right? q upon 2 epsilon naught, right? So flux through each q will be nothing. It will be q upon 2 epsilon naught. Now let's try to solve this problem third. The problem third here is like find the total electric flux through a shaded face of the cube, right? We have to find the total electric flux through the shaded face of this cube. And in this situation, we have placed a charge q at the center of this cube, and we have also placed a charge q at the corner of this cube, right? At the corner of this cube, correct? So let's suppose that because of this charge q placed at the center of this cube, because of this charge q placed at the center of this cube, the flux through this shaded surface will be nothing. It will be equal to q upon 6 epsilon naught, right? But now we have to calculate the total flux because of this charge q, which is placed at one of the corners, which is placed at one of the corners of the cube, right? Let's suppose that this is our square here, right? This is our square here, and we are placing a charge q here. We are placing a charge q here. Is the charge q. Charge q at a height of a. Charge q at a height of a. So the charge q has been placed at a height of a, right? This is placed at a height of a. And we know that suppose that uh, if we complete this square, if we join three more squares to this square, right, like this, these are the three more squares added to this, right? Three more squares added to this. It means that it's like the charge q now placed at a distance of a by 2 above the a by 2 above the one of the faces of the cube, and we know that the electric field because of electric flux because of the uh, charge q passing through each face is nothing. Let's assume that this is the complete face of a closed cube, right? These four squares represents the complete face of a whole cube. It means that through all these four squares, the flux will be nothing. It will be equal to q over 6 epsilon naught, right? It will be q over 6 epsilon. It will be q over 6 epsilon. But the flux, this q over 6 epsilon naught flux will be distributed among the four smaller squares, right? It will be distributed among the four smaller squares further. That means that the flux through this square will be nothing equal to, that will be q over 4 into 6 epsilon naught, right? It means that flux through this smaller square is going to be equal to q over 24 epsilon naught, right? Q over 24 epsilon naught. In the similar way, the flux because of this charge q placed at this corner, through this shaded portion, right? Through this shaded portion, this is also going to be equal to flux because of this corner, right? Phi c, that will be equal to q over 24 epsilon naught, right? Now the total flux because of both the charge, one charge placed at the center of this cube and another charge placed at the corner of this cube, will be the sum of the both flux. That's phi will be equal to phi center plus phi because of the charge at corner, right? So the total flux will be q over 6 epsilon naught plus q over 24 epsilon naught, right? The net flux will be phi q over 24 epsilon naught. So this will be the net flux through this shaded portion because of the charge q placed at the center and the charge q placed at the corner, right? So that's it for today, and in the next class we'll be discussing more about the Gauss law, and we'll be also discussing about three different symmetrical cases of the Gauss law. We'll be talking about the spherical symmetry, cylindrical symmetry, and the plane symmetry as well. Till then, take care. Goodbye.